Today is the seventh session of our lecture series, and I would like to invite our former civil section committee chair, Engineer Mrs. Kamala Gunawardena, to do the welcome. Over to you, madam.
Yeah, good evening. Thank you, Inji Vanduka. It's my pleasure to welcome you to this lecture series, actually, especially for today's lecture. Yes, it's the seventh lecture on the session for this session and the continuation from the previous lecture. I'm correct, no, Vanduka?
Yes,
Yeah.
yes, madam, correct.
It's a continuation from the last lecture. So let me welcome our esteemed Professor Tishan Jayasinghe, for this lecture today and all the participants who are joining here for this lecture. If I tell you a little bit about what Professor have done so far, many of you may have been joined with us in the previous two sessions. Also, Professor conducted like in 21, 22, you did more than 20 lectures on high-rise building using Eurocodes. And in 22-23, you completed about 17 lectures, including one physical, which was really remarkable for us. And that also under highway bridges and structures using Eurocode. So deviation from that, what I see is now. And participants, you are very much fortunate this time to join these lectures on structural designs of cost-effective, lightweight, hybrid ones, multi-story buildings using Eurocodes. So it's actually what I feel is very much a great opportunity. Also, I understood that Professor is giving knowledge on value engineering, highlighting that if you give opportunities to QA, QC engineers and to optimize the structural designs with that input. Thank you, Professor, for your great contribution towards the membership of the ISL. And I would say it's a unique person, unique resource person who is doing this so far, and I appreciate it. On behalf of the Chairman Civil Engineer Sectional Committee Engineer Mangal Silva, once again, I welcome everyone to the lecture and hope you will fill up your baskets with some important stuff from this lecture as well, right? Without further ado, I invite Professor Tishan Jayasinghe to take over the platform. Thank you.
Thank you, madam.
Professor is muted, Banduka.
Yes,
I'm not allowed to unmute. My phone has to be unmuted.
let me check, madam. Nice. Let me check, sir. Can you try it again, sir? Function is given from me.
Bandhu, still I am not allowed to unmute my phone. I have two contacts.
Yes.
One is the phone.
Yeah. Other one is name is
Other one is the
MTR
computer.
Jaising.
The main one with the camera.
Yeah.
Sorry?
Now I'm talking on the computer, but phone is better.
1 minute.
Professor's volume is little low, what I feel.
Yeah, so I'm talking on the computer. That's the problem. If I talk on the phone, it's okay. So you have to allow unmute me on the phone. I have two contacts.
Yeah. Yes, sir. One is name is MTR Jaising and the other account is Tishan. Is
Tishan,
that correct, sir?
co-host.
Tishan Jaising. Tishan Jaising is, I think, maybe phone.
Yes.
I'm not sure.
I have made both accounts as co-hosts. It should be possible. I will check with Chamar as well. 1 minute.
Until it comes, I will talk on the computer. Can you hear me?
Yes, we can hear you, sir. I will check the other accounts.
Yeah. So sometimes this computer does not work well. That's why I. If you can hear me, I'll continue until this is sorted out. Is it
We can
okay if
hear.
I continue?
Yes, we can hear you, sir.
Yeah, if you have
Meantime,
any
I will.
problem in hearing me, let me know.
Okay, sir. I will check what happened to the other accounts.
Yeah. Okay. Right. So last time we talked about doubly reinforced beams. And then I showed you, in doubly reinforced beams, we get a lot of reinforcement in compression zone. That is not economical. But if you have a flange, large flange, then we can make it economical. So we talked about flange beams. And I showed you how to design a flange beam and how we decide the depth to the compression zone, and we have to make sure the compression zone is inside the flange. Can you remember those?
Yes, sir.
Right. So basically what I said was, if you have a huge moment, a moment greater than given by 0.167 FCK BD squared. If the moment is greater than that, the depth to the neutral axis is 0.45 D, and we'll need some reinforcement to carry the moment, and we'll have a moment M1 greater than M max. M1 minus M max is the extra moment, and it has to be carried by the compression reinforcement is dash FYK divided by 1.15 multiplied by D minus D dash. So this says force multiplied by lever arm. Multiplied by lever arm. So today is 17 1/2024 Civil Engineering Sectional Committee lecture series lecture 7 and page 1. So we need extra reinforcement, and this is D minus D dash, and that reinforcement can be found S dash M1 minus M max divided by 0.87 YK D minus D dash. So straight away you can find the extra reinforcement needed for the beam to be doubly reinforced, because the moment exceeds the maximum moment capacity as single reinforced. Then I said, okay, these are not economical. Why? Concrete is a cheaper material, steel is an expensive material, so we should not use steel to carry bending moment. So what is better? Flange beam. But the important thing is S or depth to the compression zone must be inside height of the flange. Is that clear, Bandhuga?
Yes, that is clear. So I checked with our IT, ISL IT department. They told that it might be some issue in the from computer, and because they have given all permissions like that, something they said. Anyway, sir, we can clearly hear you from now
You can
now as
hear, no need, no problem, no need to have a phone, so I can continue.
Okay, sir.
Your background muted, your video is stopped. Doesn't matter, I mean, this is working today, we will continue like this.
Okay.
Right,
Sir.
okay. So, now the question. We have a continuous beat. So, this is a continuous beat. So, how does it deform? Deforms like this. So here tension in the bottom, tension at the top, tension in the bottom, tension at the top, tension in the bottom. So here, if it is flange beam, here your tension. So what is effective is only this. Here, tension is here. What is effective is this. That means it's a flange beam. In the span flange beam, over the support, rectangular beam. Is that clear, Bandhuga?
Yes, that is clear, sir.
Right. Okay, excellent. Now, we have let's look at the scenario. These are beams. So you get these as L1, L2, and so on. Sorry, B1, B2. We say B1, B2. Right. So this is a plan view. And the slabs are like this. Then we have the supports. And these supports are the same as these ones. These are supports. So the beam is continuing like this. So these are L1, L2, L3. Now, what happens is, we have an effect called shear lag. And shear lag makes plane sections not plane. Plane sections not plane. What do you mean by that? What is the meaning of that? You have learned this formula. What is that formula? The famous Bernoulli equation. We generally call it Bernoulli formula. And here, what is the assumption? Plane sections remain plane. Strain diagram like this. But what happens is, this bending somewhere here, if you draw the stress distribution in the flange, it will take a shape like this. So that means You can't say the stresses are uniform in the flange. They are more close to the support or the beam. So we say we have an average value, but we have a restricted width. Because from center line to center line, we can't take it. This center line, this is the center line of the slab. We can't take center line to center line because on the center line, the stresses are very low. So we say plane sections do not remain plane away from the beam. Plane sections do remain plane only at the beam. And we call it shear lag. Have you learned shear lag, Bandhuka? Shear lag?
Shear lag.
Anybody who has learned shear lag, please respond. If you haven't learned about shear lag will make the plane sections not plane. That means the stresses are not uniform. They are like this. On the flange, they are like this. So we cannot use the full distance from center line of the slab to the center line of the other slab. We have to have a restricted. So this in the British code, finding the flange width is very, very easy. So as in Eurocode, but Eurocode little complicated, but there's nothing in it. So what the Eurocode said was, you get L1, L2, L3. So if a flange beam here, it will be web width B flange is equal to BW plus 0.7 times L1 by 5. If it's an L-shaped beam, slab only on one side, B flange is equal to BW plus 0.7 L1 divided by 10. Very simple. Now you might ask, what is this 0.7 L? You draw a bending moment diagram. 0.7 L is the distance between point of contact flexion. Here it should be 0.85 times L. There should be 0.85 times L. Distance between zero moments is called .7 L. It is equal to 0.7 L. They have considered it as equal to 0.7 L. Is that clear, Bandhuka? I think Bandhuka is disconnected. So can somebody else tell me whether it's clear?
Yes, it is clear.
It is clear, sir.
Good. Yeah, please give some feedback because I'm little concerned whether I have lost the contact.
Okay.
Right? So when I ask a question, just say yes or no, even that is enough. Right?
Okay, sir.
Okay.
So Bandhu, my connection was lost and I just joined
Yeah,
again.
I thought your connection is lost.
Okay.
Yes.
Okay, sir.
Right. So now Eurocode is different. Eurocode has brought a lot of other parameters. In Eurocode, BF depends on BW as a function of B, BI as a function of LI. In British code, it's a function of span of the B. But in Eurocode, it's a function of the distance between the beams and the distance between the supports. So this is distance between beams. This distance between supports. Eurocode also gives the same diagram. It cannot change because it's from fundamentals. This 0.85L. This 0.7L. So each one of these will be 0.15L. Here also it will be 0.15L. Here also 0.15L. Here also 0.15L. Okay, got it? Bandhuga? Right. It looks like Bandhuga has again lost connection. Right. Now I'm going to share the screen. Here you go. It gives a lot of diagrams, right? So effective flange, width of flanges, all limit states. Can you see 0.85L, 0.7L, 0.85, 0.15L, or the support? And these for a cantilever. The effective, the length has to be taken as 0.15 L2 plus L3. So it says 0.2 times B1 plus 0.15 is L0. But should be less than 0.2 times L0. So B effective from one side. So what it says is, if I write it in simple rule, B flange is equal to B width, B web plus 20% of distance, 20% of span of the slab, plus 10% of distance between point of contraflexion. So for an example, let's say we are having a beam going like this, and these are 4 meters, let's say 5 meters. This span is 7 meters. The typical situation, this span is again 7 meters. Or let's say internal span is 8 meters. So what is the flange width from this side? This is the flange beam. What is this side?
Sir, excuse sir, we couldn't see the notes, sir.
Oh, yeah. Okay. Hang on. Yes. Sorry. It's good that you told me. Right. So so the rule is F is equal to BW plus 20% of span of the slab, 20% of distance between point of contact. So what is this side? So BF left, I'll say left, is equal to 20%. 20% of 5 meters. 20% of 5 plus 10% of distance between point of contraflexion, 0.7 times 7.1. but has to be less than 20% of 0.7 times 7. So let's calculate. Madhu, what is this? 1/0 plus 0.49 should be less than 0.98. Is that right, Bandhuga? So what is governing then? This 20% of rule is governing. Is that right, Bandhuga? 20% of 1 is 1. 20% of 5 is 1. 0.7 into 7 is 4.9. 10% of 4.9 is 0.49. And 20% of 0.49 is 20% of that is 0.98. So 1.49 should be less than 0.98. So which is governing? 0.98 is governing. So the width of the flange beam is, say, this 300 millimeter rib. So this side 0.98, this side 0.98. So 9898, so 1.96, 2.26 meters. Is that clear?
Yes, sir.
Right? Because it's symmetrical, I have considered same value on the other side, so altogether 2.26. So if you look at the diagram, it's very, very complicated. So don't look at it too much. Just memorize the rule. Because, you know, see this diagram? Lot of things. So you have a diagram, you have a lot of equations, and then this diagram. But the meaning is simple. So what would you use? The rule like this or the code? To me, this rule is very simple. So we know 20% comes from the slab, 10% comes from the wing. What do you think? Is it easy to remember or difficult to remember? But the total contribution cannot exceed 20% of the beam. That's on one side. So other side also, most of the time they are symmetrical, so you can just add up the same value. What is the opinion? This simple rule is simple, or you want to look at the code? I prefer the simple rule.
Simple rule is easy, sir.
Yeah, because you know, now if you are a good designer, you should have all these rules in the code in your brain, stored properly. So you don't have to turn to pages in the code and waste your time. Right? You are a good designer. All the rules are known to you. So even without using the code, you can still design. That's the level of ability you have to develop. So I prefer rules. Why? Rule will allow us to forget about the equation. Okay.
Okay, sir.
Right. So now let's say this slab subjected to a load of 13 kilonewtons per meter squared. What is this magic number 13? 1.35 GK plus 1.5 QK. Now how do I get this magic number? For a house, what is the magic number? 8 to 9. For an office building, what is the magic number? 11 to 12. If you have extra loads in the office, It can be 12 to 13.
Biofuels supplied 3% of the energy used worldwide
Auditorium,
for road transportation in
12
2011.
into 14.
In the United States, which is the largest biofuel producer in the world, biofuels generated 4% of the energy used for transportation in 2011. In 2009, in Brazil, which is the second largest biofuel producer in the world, a total of 23% of the energy
Engineer Nalin,
came from
you
biofuels.
are unmuted and some disturbance coming.
Now I think I am unmuted. This is working.
Yeah, now very clear, sir.
Now very clear.
Yeah.
Right. Yeah. Now clearer?
Yes, sir. Now clear.
Yeah, okay. Well, I have turned off the computer, now I am on phone for sound.
Okay,
For
sir.
video, I am on computer. So then it works well because I can monitor what's going on. On the phone, I can monitor what's going on. Otherwise, I don't know what you see. Now on my phone, I can see what you see.
Okay, sir.
Right? That's why I use two devices. Otherwise, I talk and I don't know what you see. But on my phone, I can see clearly what you see.
Okay, sir.
Right. So that's a good strategy. Even if you are doing a presentation, use that strategy. Have two devices. For the audio, use the phone. For video and all the other stuff, use the computer. Then on your phone, you can see what the other people can see. What your audience can see, you can see on your phone. Then you can keep a track of what's going on. It's very easy to do it that way on when you are doing a Zoom lecture. Right, so now
Okay,
let's look at the example. Same example. What is the load? Load is 13 kilonewtons per meter squared multiplied by WL squared or 10. 7 squared divided by 10. What is the moment like? 13 into, Bandhu, what is this answer? 13 multiplied by 7 squared divided by 10?
8.1, sir.
No, it's 13 multiplied by 7 squared divided by 10.
1 minute, sir. 1 minute.
200 something.
Seven square divided by 4.
10. WS squared or 10.
Okay, sir.
Oh, but you
63.
have to
60.
multiply this by 5. Multiply that by 5.
Yeah.
5 into 13 multiplied by 7 squared divided by 10. Some 200 something.
318.5.
Yeah, 18.5 kilonewton meter. Now let's say that is the moment in the span. So we have flange beam. What is the flange width? 2.26 meters. We calculated it earlier. Can you remember I calculated it? Yes. 2.26 meters. Okay? I
Yes, okay,
calculated it.
Yeah.
Right?
Yes, sir.
Now, you want to design this flange beam. And I will assume that so how do I design it? I have to find MOBD square. I am using the shortcut method. No? 318.5 into 10 to the power 6 divided by breadth 2260 multiplied by, now this is 600 millimeter deep. This 600 is a magic number. You generally don't use a beam depth more than 600 under normal situations. Even up to 9 meters, you will increase the width of the beam and be happy. And D, generally you don't get spans more than 9 meters in a reinforced concrete building. Maximum span is 9 meters. Because you know, beyond 10 meters, the design is also very complicated. It has additional deflections and all kinds of problems. So generally we go for a maximum span of 9 meters when you are selecting the grid, because 9 meters itself is about It's huge. It's 30 feet span. So depth is 545. What is the value? What is the answer?
48.
No.
48.1.
Sorry? 545 squared Bandhu. Maybe 2.1 or something like that. The answer should be around 1.8, something like that.
So, it's
1.2, something.
0.47. 0.47.
0.47, that's right.
Yeah.
Then what is 100 days of BD? Divide this by 4. 0.12. Okay.
Yes, yes.
Then what is A? A is 0.12 multiplied by breadth 2 to 60 multiplied by 545 divided by 100. What is A?
1,478.05.
You will write 4 numbers, 3 numbers of 25 diameter. 3 numbers of 25 diameter. Or you can write 2 numbers of 25, H25, 2 numbers of H20. So that is 314 into 2. This 490 into 2. What is the total area?
$1,608.
When we need 1,170. Is that clear?
Yes, clear, sir.
Now, if I select this one, 190 into 3, 1,170. Marginally low. Now, why do I select? If you want, I can select this also, because if I do a proper calculation, this will be okay. Because I use slightly higher 0.12 instead of something. So 1,170 is also okay. But I select 1,608. Why? Why? Because I always provide slightly more reinforcement in the span section. What is the reason? Beams never fail at the support. Beam fails only at the span. So in the span, no harm in providing some extra reinforcement. Is that clear, Bandhuga?
Yes, clear, sir.
That's the reason. So now we have to make sure S is less than HF. So I say area of reinforcement. Force in concrete is equal to force in steel. So what is the force in concrete? 0.587 F YK multiplied by breadth 2,160 multiplied by S is equal to 0.87 FYK multiplied by 1,178 is the area. From this I can calculate S, because FYK is 30, FY is 500. This 500, this 30. What is the only unknown? Only unknown is S. Then you can find the value of S. You might get about 40 millimeters. What is the value for S, Bandhuka?
Wait, sir.
You might get about 40 millimeters.
$16.15, sir.
60?
16.15.
16.15.
0.87 into 500 into 1478 divided by 0.587 into 30 into 2260.
60, yes. This is very low, huh?
Yeah. 16.15.
Doesn't matter. What the requirement is, it has to be less than H,
Yes.
right? Okay. So now you provide this reinforcement. Will it ever fail? It will never fail, provided that you include some reinforcement here across the beam, so that no shear failure can occur here. So I have not covered shear to teach you how to find this reinforcement, but for the time being, we'll say we are going to provide some top reinforcement anyway, and then when you are providing the bottom reinforcement, what do? My detailing is I continue this reinforcement here, I continue this reinforcement here, so there's full lap here, and that will also provide some extra resistance for shear cracking. So I will provide top reinforcement and bottom reinforcement, but top reinforcement is continuous, bottom reinforcement has a joint, but the joint is done properly so that there's plenty of reinforcement across the flange to make sure the flange never fails. Is that clear, Bandhu?
Yes, that is clear, sir.
So I will not just provide, to the middle, but I provide to the very end on the beam, right? And if you make a small bend also, that is even better. Then it has better, and then the flange will never ever fail. So you'll have a super strong beam. Is that clear?
Yes, that is clear.
So I have covered flange beams, doubly reinforced beams, singly reinforced beams. So beams are over, I think. Is that right?
Yes, correct, sir.
And also I explained moment redistribution. So everything on beams have been completed. And we can start shear today.
Okay, sir.
Right. So I will actually talk a little bit about torsion also. Shear can be many different types. Because, engineers generally don't have much idea about torsion. So it's better to tell something about torsion also when you talk about shear. Then we have a beam. We load it. So we are applying the load here. Where are we resisting? Here. So we must have shear. And always flexure is associated with shear. But there's another type of shear. Let's say we have a beam, we have a slab here. Slab is cantilevering from this one. And beam is like this, connected, it's continuous. Slab is only here. What happens? When you load the slab, what do you get? Moment like this. And what is the axis of the moment? Axis of the moment is like that. Along the beam. Any moment where the axis of the moment is along the beam.
Engineer Senaviratna, your mic is unmuted.
Stroke or torsion. Now, where can torsion happen in a beam? Let's say we have a transfer beam, 1.5 meter by 1.5 meter beam. And where the axis of the beam? Here. Center. And we have a wall here. The load from the wall is coming here. Why are we using transfer beams of 1.5 meter by 1.5 meter beam? Because we are supporting few floors. Or a wall supporting few floors on the transfer beam. So there's a massive load. Maybe about 2000 kilonewtons. Distance, these 0.75 meters, this 200 millimeter thick wall, so this 0.65. So 2000 kilonewtons into 0.65, what is the value? 130 kilonewton meters. So what can I say about the beam? It's a massive beam, 1.5 meters by 1.5 meters. Still it's subjected to torsion. We call this equilibrium torsion. Why? If you do not provide torsion or reinforcement, beam fails. Do not provide torsion or reinforcement. Beam fails. Why? Because this can create a massive torsional stress. If the torsional stresses are too high, you get diagonal cracks forming right around the beam. And the beam can fail. We must make sure beam would not fail like that. So, how many shear forces? One is direct shear, the other one is torsional shear. Two types of shear forces can act on a section. And we must make sure both are resistant. But when you do perform structural analysis by using a 3D program, you get bending moments on the beams, you get shear forces on the beam, direct shear, but you hardly get any torsional moments. Why? Because we are applying most of the loads on the axis of the beam. We don't apply loads away from the axis of the beam. So you don't get torsion. So you don't have to provide a design for torsion, you don't have to provide extra reinforcement for torsion. But minute amount of torsion can be there which can be easily resisted by concrete. Is that clear?
Yes, that is clear, sir.
So I'll show you a note. I'll show a note. I'm going to share again. Okay, torsion in beams. And this is an extract from book Reinforced Concrete Design to Eurocodes by Bart, McGinley and Chu. Very good book. But don't read it immediately unless you are familiar with Eurocode. The first book to read is not this one. What is the first book to read? The Reinforced Concrete Design book by Mosley and Bunge. Read that first.
Then when you are familiar with the subject, you can read this one. It's an advanced book, very good, excellent book. But if you read it for the first time, what will happen? You will give up reinforced concrete design. So this is very complicated book, right? So don't read this for the first time. First read the book by Mosley and Banji. Once you understand reinforced concrete well enough, you can read this one because it covers a lot of advanced technology. So this note is based on that. So here, what do you get? Equilibrium torsion. What do you get here? Two interconnected beams, and it is compatibility torsion. Now, when you connect two beams like this, even if you don't provide torsion and reinforcement, it will never ever fail. So it's called equilibrium, compatibility torsion. But if you don't provide torsion and reinforcement here, it will fail. It's called equilibrium torsion. And this theory is used very much when you are analyzing M beams and Y beam bridges. We say they are torsionless systems. The reason is what you get in a M beam or a Y beam is a compatibility torsion which can be taken into account by having a higher bending moment than anticipated on normal calculations. So we provide. So what we do is we simply in beams of Y beams or M beams in a bridge, we say we are going to have compatibility torsion, and we say the torsional constant is 0. The moment you say torsional constant is 0, you get higher bending moment. You get a higher bending moment in the beams, and you design for the higher bending moment, higher shear forces, and finally you find, though you are not specifically designed for torsion, you are okay. You're okay. So this is a method that we use in bridges a lot. And so the torsion shear stress in a concrete section is like this. And then if you have
Engineer Chalani, you are unmuted.
And if you have a open section like this, the torsion and shear stresses are given by this equation. So those are not very important for you just to understand. So what you do is when you have a rectangular section also, according to Eurocode, we consider it is a hollow section. It is a hollow section. And we do the calculations. This diagram is directly from the Eurocode. And then when you are designing for Eurocode, you can see the type of diagrams you have to see and the type of equations you have to fulfill. Very difficult to remember all these, recall all this. So what do? Very simple. What we do is, all the theories are given, lot of equations. What are you going to do? Look at the example given by McGinley in design for torsion. So the example is included. The moment you look at the example, you will understand how to deal with torsion and deal with it in that way. So torsion is not a major problem. You can see there's an example, and so in the example, how to do the calculations are given. So what you have to do is go through the example, try to understand the method given in Eurocode, because if you try to understand this, you will never understand it. What is this? This is a code. Mandu, can you understand this kind of complicated stuff? What do you think, Mandu? Do you like all these complicated diagrams and equations?
No, sir, it's very difficult to understand.
Yeah, it's a killer. You don't do it. Then what do? Forget about all that. So just go through it just to understand
what are the provisions? So all these are provisions, and then go through the example. So go through the example. Then you'll understand it's not that difficult, right? So
means
in the
if we
equation example also, yeah,
if
I
we
have given
directly
equation.
yes sir, if we directly go to the example and
Yeah,
then
yeah,
it will be
directly go
easy.
to the example. No. Just look at the code before. Just
Yeah.
glance through it. You don't have to understand, but you should make your eye used to it. And after that, go to the example. But in the
Okay,
example also, I have given the code extracts. The equations are given. I have modified the example. I have taken things from the example, put things in between from the code so that you will understand what you are doing, right? And then, so that's all. So you can put it on the computer. You can write a spreadsheet for this. Otherwise, doing a torsion calculation is a killer. I mean, very difficult if you try to directly use the code. Why? Code covers all possible scenarios. But when you are designing a beam for torsion, it's not a big deal. So what you do is you will go through the example and put it on a spreadsheet. So whenever you see a moment, you put it to feed the moment with the dimensions, then the rest can be calculated. Got it?
yes, got it, sir.
See? Lot of calculations, lot of theories, a lot of proof, lot of things. So I have put everything inside so that when you are doing the calculations, when you are using the equations, you will understand why you are doing it. So whatever relevant is in the note, right? How those equations are derived, everything is in the code. From the code, I have given small information. It's very easy. You have to just go through the example. Right, so I think we have shared this note, Bandhu.
Yes, that is in our Google Drive.
Yeah.
Anyone
So
can
please go through the
access.
note. It's a very easy to understand note, not a difficult thing. It has an example. Just go through the example, and within the example also, I have shown the relevant equations. So you can easily follow it. Right, in the textbook, the theory is at one place, example is at a different place. What I have done is I have put all together so that you can understand the theory and the example all in one go. So
Thank
that
you, sir.
is
It's a
torsion.
very valuable document, sir. It's
Yeah. So please go through it because very difficult to teach these things. These are the things engineers should read and understand. Okay, but a very good document is available for you to understand. It's better than the textbook now, right? So go through this note and try and understand how do you do torsion, but you have to understand torsion comes only where? Transfer beams. If you are designing a transfer beams of a 30-story building or a 20-story building, you have a transfer flow, then you must be very careful. You must be very careful in modeling. Later day, I'll show you how to do the modeling, right? And then how to do the modeling to get the torsional moments. I can show it now itself. Just give me a small time. Just give me 1 second until I open the document.
okay, sir.
Okay, I'm going to share the screen again. Now you can see structural design of tall buildings. Can it be rule based? Can you see the title? Can it be rule based? Can you remember I told you rules?
Yes.
So what I say is, you don't need code. If you ask me to design a 30-story building, Bandhuka, I will ask you to keep all the codes with you. I say, I don't want codes. You keep the codes. And within 1 week, I don't have a code, but still I can give the whole design in 1 week with a challenge. What is the challenge? If you find a single mistake in my design, I'll give you 10% of the design fee. And if you find 2 mistakes, 20%. If you find 10 mistakes, I don't get anything, you get everything. Right? And then I'll say, if you optimize my design by 10%, I'll give you 10%. If you optimize my design by 20%, I'll give you 20% of the fee. Right?
One question, sir.
Okay.
So how to improve ourselves for that to do
That
those
level?
designs?
No,
Yes,
no,
sir.
you have to read. You have to read the books and read the books early in the morning and see how the equations are derived. And then you have to see what is the rule relevant. You make your own rules. So I have made my own rules, so I don't need codes. I can do all the calculations without having a code. Because all the input technical data is I have stored in the brain. So I can do all the calculations without looking at the code. Got it?
Got it, sir. Thank you.
Yeah. So that has to be, you have to work hard on it. But it's worth. Why? You go for a presentation, or you go for an interview, or you are at the site, you can simply run the show. Right?
Yes,
so
sir.
this presentation I have given. This is a presentation I did in Liverpool University on 27th February 2019, before we got COVID. 1 year before we got COVID, we were in Liverpool University as visiting academics, and I did a presentation, and the students could not believe what they heard when I told them I can design without codes. I use my own rules. They could not believe, but they have never heard a person who says, I don't want codes. Everything in the code is in my brain. Nobody has ever told them that. So you can see Altair. See, 43 floors without a support. 43 floors of inclined building without supports. I've seen this before. 43 floors, no connection. In the actual building, there's a connection, but up to now, there's no connection. 43-story building completed, inclined. Right? So I have actually checked it, whether it can be okay. So we had a model where we did not have, we had only up to this player. So these are the, pre-stressed concrete balconies of Clear Point. Another landmark building. Right.
So today what happened was actually I lost the host because of due to some unstable connection.
Yeah.
Now I can't control the members.
Right, okay. Now, Bandhuka.
Yes, sir.
Now we are going to come into a very important thing. So, can you see some of these walls starting on the edge of the beam?
Yes, we can see that, sir.
Yeah. So that's where you get torsion. So you can see how I have done it. So here this is the center line. Can you see a small arm here? You can see a small arm.
Yes, sir. We can slightly see that.
You can see the arm. So
AM 16342. You are unmuted.
Right. So you can see the small arm. Can you see here also? You can see the arm. So
yes, sir. We can see those arms.
It's called a strong arm. Strong arm is a big section. It's used as an arm so that we can place the shear wall at the correct location. Wall is at the correct location, not on the beam. So when you do the modeling that way, you can see that. So can you see here? All these walls, can you see they are not on the center line? They are not on the center line. And how to get them not on the center line? So this extruded view, you see it not on the center line, but it's no problem. But on the model, there's a problem. The problem is solved by having strong elements or strong arms or rigid arms connected to the beam. A rigid arm is here. Here you can see some places there will be rigid arms, right? So here you can see rigid arm.
Can you explain it again, sir? How it was?
No, actually, now you have a wall.
Okay, sir.
In the upper part of the building. It is not coinciding with the center line of the transfer beam.
Yes, sir.
It's on the edge of the transfer beam.
Yes.
Now, in modeling, what is the dimension of a central of a beam? It's a central. It's a line only. It has no dimension in the model.
Yes, sir.
But in the actual structure, it has a dimension. So what you are modeling is the center line. What you are modeling is the center line. Is that right?
Yes.
So when you say beam, you place a beam on the center line, but you are at the wall. It is not on the center line. So we need a member to connect those two. And those are called rigid arms.
It's
rigid
acting
arms
like
a very large section rigidly connected to the beam on the center line.
Okay, sir.
Got
so
it?
we have used rigid links to model that
It's
action.
not a rigid link, it's a rigid arm.
Okay,
it's like arm. Something projecting out. That's why you call it arm. Arm is projecting out from the shoulder. It's like an arm. Right?
Okay, sir.
Rigid arm. Why you call it rigid? It has a big section. Got it?
Okay, clear, sir.
It has a big section, we call it rigid. We call it arm because it's projecting out from the center line. So we call it a rigid arm. When you put a rigid arm, you can put the wall in the correct location, actual location. Got it?
Got it, sir.
So when you extrude and see, you don't see it. You see the walls in the actual location. Can you see edge of the beam?
Yes, sir.
But in the
extruded
model,
view,
it is not the edge of the beam. We have deliberately created the location at the edge of the beam. Deliberately. Otherwise, it will appear on the center line. Then it's wrong. When you analyze, you don't get a torsional moment. When you put anything on the center line, you don't get a torsional moment when you analyze. If you want any torsional moments, there are torsional moments, actual moments. If you want to find the magnitude, you must put the members at the correct locations. Then only the torsional moments will be generated. Is that clear?
clear, sir. In this extruded view, our rigid arm and the beam extruded parts are coinciding. Is that correct?
Coinciding, so you can't see it actually.
Okay, sir.
Right? But extruded will clearly show you that they are not on the same line.
Yes, sir.
That's the important thing. Right? So these are trick. Very valuable trick for designers. So you can see this is something I have shown you already. There's another important thing. Can you see the piles?
Yes, we can see, sir.
And the pile cap?
Yes.
What is this building? This is a building at Nugegoda called Porsche, close to what you call Valley Park. On the Open University Road from Nugegoda, Supermarket Junction. On the Open University Road, there's a road connecting to Pagad Road. And just after that, you get this building on the left-hand side. It's a 14-story building. So you can clearly see, I mean, we have model foundations, piles, foundations, columns, beams, transfer plates, transfer beams, the walls above, everything in one go. Very advanced modeling. Using what? SAP 2000. Simple program, but very complicated model has been made. Is that clear?
Yes. Yes.
So, do you have ability to create a model like this? If you don't have, don't worry, I'm going to show you later. I have the license for SAP 2000, so I'll show you how to use SAP 2000 to create a model like this. And that's where the money lies. Because if your ability to create a model like this will make sure you are eligible for big payments. And the other important thing, you can see the transfer beam is coming and connecting here. You will find the bending moment on the column is much higher here than here. So what will happen? Where will you get the highest reinforcement in the column? At the bottom or at the top? Just below the transfer level, you might find the reinforcement needed in the column is much higher than the reinforcement needed at the bottom of the column. Have you ever heard something like that? The reinforcement needed at the just below the transfer plate or transfer beams is much higher than the reinforcement needed at the bottom of the column. Have you ever heard something like that?
No, sir.
But it can happen. Why? Here the moment dominates, here the axial force dominates. Columns are very good in carrying axial force. They may not be very good in carrying bending moment. So you will have axial force domination here. Here what you get is bending moment domination. So when the bending moment is dominating, you might get a situation where the reinforcement requirement is higher. Got it?
Yes. Yes.
So you have to be very much concerned about all these different aspects. So that's why I thought I should touch on torsion. Otherwise, every course will touch on shear, but not touch on torsion. But now you can see torsion is a very important aspect that the engineer should master. But finding the once you find the torsional moment, finding the torsional reinforcement is not a big deal. You just look at that example and put everything onto a spreadsheet. So you feed the numbers in, you will get the answers out. Is that clear, Bandhu?
Yes, that is clear, sir.
Yeah. So dealing with torsion is not a big problem. What is the problem then? Creating a model where you will find the torsional moment. To create a model in such a way that the torsion moment is given by the model is a challenge. So that you have to take head on, and here in this example, I have done that. So this is a very useful presentation to go through. Have you got a copy of this presentation, Bandhu?
Sir, until now, we haven't shared this one with our group. Maybe I might be having this. Okay, sir. Thank you.
Please share it, because that will be useful for all the, because it covers a lot of ground on every aspect is covered, including DEF that we covered earlier. So
Yes.
you better share it. And this is Monarch, Crescent Monarch. Here you can see the transplate, because the building was originally completed only up to 4 floors. Later they added some 22 or 23 floors. And originally meant for an apartment building, later it became taller. Originally as an office building. Later it became an apartment building that needed strengthening of the columns and so on. Already cast columns. So this is another landmark building where again I did a lot of work. where this upper part had so many shear walls, the transfer plate was solid, so I made it a cellular transfer plate that helped them to a lot to the company was building their own building, and they were losing a lot of money because the design had too much reinforcement, and we had to make it lightweight. So I did it with a model, and this is cinnamon red. Okay, the transfer plate is at the 10th floor level. Just imagine casting 1.5 meter thick slab at the 10th floor level. It's a huge task. So what I did was I made it all cellular transfer plate, where most of the material unwanted was removed, and I made it a beam slab structure, but I put a slab at the bottom, slab at the top, so it became a cellular structure, a hollow structure, and that way we save a lot of reinforcement, lot of money, lot of concrete, and we made it robust. The load on the foundations were reduced, and finally the upper part also optimized a lot, resulting in a huge saving for the owning company, which is Sunken Lanka. So they are the owners of the building, but management is Cinnamon, so that's why we call it Cinnamon Red Hotel, but owned by Sunken Group. So that's another very important project that we did, and did the infinity pool at the top of the building. On the 26th floor, you get an infinity pool. You can see almost a lot of nice sceneries of Colombo, including sunrise with behind Sri Pada early in the morning. Very nice scenery. So there's a lot of information that is useful, and how to model the foundations using springs, and so a lot of useful information. And with that, shall we wind up so we can start the proper shear, the flexural shear design next time? Bandhu?
Okay, sir. There are few questions.
Yeah. What are the questions, please?
Yeah.
What is the first question? Link, no problem. Okay. Please don't interrupt the session. Mute your mics. The connected walls and frames have to be weightless. Yes, they have to be weightless because they are additional members. They have to be weightless. Rigid links to support the eccentric walls. What property modifier should be used? So basically, either you can use a small beam, multiply the I by 1000. On the other hand, you can use a big beam, and if you are using a big beam, you don't have to multiply anything. So one good thing maybe use a lightweight rigid arm, and multiply the I value by 1000. Second, go to set modifiers and multiply the I value by 1000. When modeling rigid links to support eccentric walls, what property modifiers? Yeah, property modifiers are needed only if you are using a small section. Otherwise, if you are using a large section, no property modifiers. Vanduga, have I answered all
Yeah.
questions?
One more question, sir. Actually, two. One is, what are the detailing rules for torsion? How torsional reinforcement should be provided?
So don't worry. That is given in the example.
Yeah,
right?
that document. Yes.
Yeah, so just go through the document. The example gives all the torsional things, requirement, and how to provide it. It's a calculation on its own. So just go through it, right? I will also explain it one day, but I just thought that because these are advanced course, no harm in giving some information early, right? But one day I will take time and explain it. Don't worry. But in the meantime, you can go through and learn, because that's the best way to learn. I mean, I can teach, but you will forget. But whatever you learn, you will never forget. Now you can see, I have spent my time. I'm teaching. Am I looking at anything? No, I can teach. So that's the same way. If you read the documents, if you read Musti and Banji, if you read McKinley, you read many other books, look at examples, try to learn. One day you will be a top expert. Nobody can ever come closer to you. But do all that early in the morning. Why? Early in the morning, there's a very special feature in your body. What is that? Your stomach is empty, brain is ready to accept data because already you have slept 7 hours. You have slept minimum 6 hours, preferably 7 hours. Your brain has rested very well. And also, the most important thing is your stomach is empty, so don't eat anything before you start working. Have a glass of water and start working. Then your stomach is empty, no sleepiness. The brain cells are supplied with lot of glucose from the body, from the heart. In bloodstream, you supply a lot of glucose. And then what happens? And then you give an order to the brain. I want you to remember all the things I do today. Because this is an important thing I am doing. What the brain will do? Yes, brain will say, yes, I am ready. And brain will store all the information that you are asking the brain to store. And you will find any day, even after 10 years, still you can recall the information you ordered the brain to store. Because if you don't order, brain will forget. If you order the brain to store the information, brain will store the information. Once it's stored, very hard to miss it. You can recall it over and over and over again if you are going to use it once in a while. You don't have to use it every day because brain is a very powerful tool and it's more powerful than artificial intelligence, much more powerful. Only thing is we don't use our brain that way. The day you start using the brain the way I have told you, you will find that you can even do better than what I do. So that's a power. So I have used the brain power because I already every day I get up 2 o'clock or 3 o'clock or 4 o'clock in the morning and I use the brain very well. And what I do is if I feel sleepy, I sleep daytime, but I don't sleep night time. I sleep night, sleep 4 hours, 5 hours, get up, work. And if there's a shortfall, I sleep daytime. But I make sure the time where the brain is most powerful, I use it. And when the brain is lazy, I sleep. So this is a different way of thinking, and we do all know I always think differently. And you can see I have used the brain also very differently. When most of the people are working, I sleep. So I sleep early. I get up early, 2 o'clock in the morning, no problem. I start working. And I might sleep daytime because if I feel sleepy, I sleep. Because why? Don't work when you are sleepy. That's why Chinese people after lunch they sleep 1 hour. Why? Because after lunch, where the blood supply? Blood supply is to the stomach, not to the brain. So if you work immediately after your lunch, your efficiency is very low. So don't work, sleep. And after that, Japanese also do that, I think. So that's why their efficiencies are very high, extremely high. So they make sure they work at the time their brain is at the best. And they sleep when the brain is not working. In Sri Lanka, our students work in the night when the brain is very tired. They sleep until 8 o'clock. When the brain is best, they have slept. That's why our productivity is so low, and that's why we are not doing well as a nation. So you have to understand it. Okay, Bandhuga.
Yes, thank you very much, sir. And yeah, one last question was there.
Yeah.
Is it needed to consider torsion at the locations of staircase connected? And
Yeah, those examples I'll show you. I'll
Okay, sir.
teach. Right, don't worry. Because whenever there's an opening, you must design that beam for torsion. And if you look at the book by Allen, the BS 8110 book by Allen, you can understand torsion very well. That's a very good book. The book written by Allen on for BS 8110, the worked examples, there Alan has given a very good explanation for torsion. Alan's book. So read Alan's book first. Then that's a best place to start. And then you can read my note. And then example. Then Musli and Manji example. The examples given in McGinley. Likewise, you have to go for comprehensive stuff. Don't go for comprehensive stuff at the beginning. The information given in Alan is the best. If you can find Alan's book and read it. The copy is available in our library. So if you want, you can scan it and share it. That particular example, explanation. Nobody is using it because it's written for BS 8110, but nobody is using it now. But Alan's copy of Alan's book is available in our library, University of Maroto library. If you can get hold of somebody who can make a copy, make a photo, take a photo and share it. It's only 2 pages. Yeah, plenty of information. Very good.
Okay, sir.
Okay.
Okay, sir. We will wind up, and next week we will discuss the shear. No?
Yeah, next week shear. Right? Yeah.
Okay.
Let's say it will be shear.
Okay.
Yes, torsion and shear. Flexural shear, torsion and shear will come back another day because when I show you how to model on-sap transfer beam, and then that day we can talk about torsion. Right? Until such time, you can do your own studies because the note is there. But next time will be flexural shear, nothing else, right?
Okay, sir.
Only flexural shear.
And also one request, sir, can we share that list of references just said, so we can.
Yeah, actually, Bandhuka, the reference is given in the note.
There is, it is in the note. Okay,
yeah,
sir.
It's here. And Musli and Manji, I think you have shared the information.
It is shared, sir. Okay. Sir.
Yeah, Musli and Manji is the most popular book for reinforced concrete design.
Yes, sir.
Everybody must read the whole book.
Okay, sir. And okay. Thank you very much, sir, Professor Tisan Jayasinghe, for conducting this lecture series. And we as practicing engineers found how valuable this lecture series is for us, and the questions coming from the participants and those feedbacks are also very positive, and they are also taking many advantages from this lecture series. So we are very thankful for Professor for sharing his expertise and knowledge with us. And also I would like to thank the Chairman, Civil Engineering Sectional Committee, Engineer Mangala Silva, for continuing this lecture series, which was started 2 years back with different topics. So thank you very much, sir. And also I would like to thank the ISL Secretariat, the Publicity Department and the IT Division for their support to conduct this lecture series. And we will meet next Wednesday, 7 p.m. with the next session of this lecture series. Thank you very much all, and thank you very